So we're going to start our study of college mathematics and statistics by looking at the basic properties and definitions of exponents. I have two expectations for you by the end of this video and assignment. The first one is that you will know the basic properties of exponents and how they are used to simplify expressions. And secondly, that you'll be able to answer how are rational exponents simplified. So a quick review about the rules of exponents. Exponents, when written as something like 2 to the third power, tell us how many times the base number has been multiplied. So in this case, the exponent is 3. So that's telling us that we have 2 times 2 times 2. The 2 here is our base, and the 3 is our exponent. So the 3 tells us how many 2's to multiply together. There are many rules associated with exponents, and we're going to examine a few of them, and I want you to truly understand the rule and not just memorize the rule. So I'm going to be working this rule out for you a little bit so that if you get stuck and forget it, you have a way to sort of bring it back to the front of your memory. So the first rule says if I'm multiplying by two numbers that have the same base but have different exponents, that you can add the exponents together. So let's think about why. If I had 2 to the third times 2 to the fourth power, remember that 2 to the third tells us that I've got 3 2's multiplied together. And 2 to the fourth power, and I'll do that in blue, tells us that I've got 4 2's multiplied together. So if I look at how many 2's there are sitting there all together, there are 7 of them. So that's the same as 2 to the 7th power. So that's why the rule has always been, if the bases are the same and it's multiplication, add your exponents. Because those exponents are telling us how many there are. So if there's 3 of them, and then there's 4 of them, and I'm still just multiplying, then altogether there are 7 of them. Another rule of exponent is called power of a power. And it says if I have a base raised to an exponent, so here you can see that I've got a raised to a power of m, and I raise that to a power of n, then the exponents m and n can be multiplied together. First of all, I want you to notice the difference between this rule and the rule that we just looked at. The rule that we just looked at, the m and the n were each attached to a base. So this n belonged to an a, and that m belonged to an a. And so altogether we added. This is a little different. So this, if I put this in terms of an example, I've got maybe 2 to the third power that I'm raising to a power of 4. So what that means is 2 to the third times 2 to the third times 2 to the third times 2 to the third. And then I could just use that same rule that we established above. Now if I go and add all those exponents, I'm adding 4 3's together. So let me write that in words. Adding 4 3's. Remember, repeated addition is the same as multiplication. So that's why I can say we'll just multiply 3 times 4 to get to the 12th power, rather than having to add each of those 3's together. A third rule that we examine in terms of exponents is the zero exponent. And many people typically remember learning at some point during their schooling that anything raised to a power of 0 is equal to 1. Most people have no idea why that's true, but they accept it as fact. So let's look at why that works. So to look at why that works, let's look back to one of the rules of exponents that we've just established. And that rule says if the bases are the same, we can take the exponents and add them if it's multiplication. So notice that I've multiplied 3 to the 5th power by 3 to the 0 power, and I've gotten 3 to the 5th power back again. So think about it. What's the only number that I can multiply something by and get the original number back? The only number that we know that does that is the number 1. That means 3 to the 0 power must be acting just like the number 1, because when we take 3 to the 5th and multiply by that, we're getting 3 to the 5th back again. Since we established that multiplication with exponents is adding of exponents, it comes naturally that division with exponents would be subtraction. But let's examine why. So if I have, let's say, x to the 5th, and I divide that by x to the 2nd, that means in my numerator there are 5 x's. And in the denominator, there are 2 x's. And if you recall, anytime there's the same thing in the numerator that's also in the denominator, that simplifies to the number 1. So we've got a 1 sitting here and a 1 sitting here. So all we have left sitting in the numerator is 3 x's, or x to the 3rd. And so that's why we're allowed to use subtraction. So let's look at the product to a power, which really builds on the power to a power that we've already established. So remember, we already said that 2 to the 3rd squared means 2 to the 3rd times 2 to the 3rd, which is the same as 2 to the 6th. So we could have just taken those two numbers and multiplied them together. So let's suppose I've got more than one item in the parentheses. Rather than a 2, let's suppose it's a 2x. Well, the same idea is going to work here, because it's going to be 2x, 2x, 2x. So I've got 3 2's and 3 x's, which means that if I have an exponent sitting outside of parentheses, it really ends up getting distributed to everything on the inside. Likewise, this same rule would apply in a similar way if it's division rather than multiplication. So this exponent would have to go to everything, both the numerator and the denominator. Rules with negative exponents can sometimes be a little tricky for folks to understand, so we're going to work through this one together. A negative exponent, you can see here a to the negative n, can be made positive by putting it into a denominator. But let's think about the y behind this as well. So if I have x squared in my numerator, and I have x to the 5th in the denominator, and I go ahead and say, well, that's 2 x's up there, and 5 x's down here, and I use the same idea from the previous slide that each of those is equivalent to 1, what we have is 1 over x to the 3rd power. Now, but let's look at the fact that we just established that we can do some subtraction with the exponents. So I should be able to do 2 minus 5. Well, 2 minus 5 gives me negative 3. So what that negative exponent is really telling you is that there were less in the numerator than there were in the denominator, because we ended up with a negative number when we did the subtraction, which means that the result was actually in the denominator. Here's another visual for that same idea. This time there's 5 x's in the numerator and 8 x's in the denominator. So if I go through and I cross out and turn to 1, the ones that match up, you can see that there's 3 x's left in the denominator. But if we subtract 5 minus 8, we end up with negative 3. Well, that's our clue that there were more in the denominator to begin with. One of your discussion board assignments for this week is actually coming off that exact premise. So I want you to do a discussion board post. I don't need you to work with a partner, but if you want to contact somebody and work together, that's fine as well. But think about how could you use division to explain why something to a power of 0 must equal 1. So let's rethink what we said with multiplication. We said that x to the third times x to the 0 gives us x to the third. And we said, well, that must mean that x to the 0 is 1, because that's the only way we'll get that original number back again. So now, rather than dealing with multiplication, think about it in terms of division. And that's what your discussion board this week will be about. So we've touched upon all of the properties of exponents that you see on this slide, really up through the very last property. And that last property builds off of the negative exponents. If I have a negative exponent, I can make it positive by putting it into the denominator. If it's negative in the denominator, I can make it positive by pulling it into the numerator. So if I have a fraction that's raised to a negative exponent, I can simply flip that fraction, and the exponent should become positive. The last rule that we established before I'm going to give you some time to really dig into this a little bit and get some practice, because we've gone over a lot, has to do with radicals, and more specifically establishing what a rational exponent means. So if we look at the square root of 9 times the square root of 9, remember that the square root of 9 is equal to 3. And if you don't remember finding square roots, think about a factor tree. 9 is equal to 3 times 3. And in a square root, I'm looking for pairs. So how many times can I multiply those 3's together to get 9? 2 of them. So that means the square root is 3. So let's look at now 9 to the 1/2 squared and 5 to the 1/2 squared. That gives me 9. And this gives me 5, because 1/2 times 2 gives me 1. So let's look back up here. The square root of 9 times the square root of 9 is 9. 9 to the 1/2 squared is also 9. So that's 9 to the 1/2 times 9 to the 1/2. Well, the only way that I can get the same answer from a problem is if these are equivalent to begin with. So something raised to a power of 1/2 is the equivalent of taking a square root. Likewise, we're going to talk later on that something raised to a power of 1/3 is going to be the same as a cubed root. Something raised to a power of a 1/4 is going to be the same as a 4th root. And we'll look at that in future lessons. So the last rule that I want to discuss in this video has to do with those rational exponents. So if I have a to the 1 over n, I can still use my rules already established and say, well, go ahead and distribute that m over. So this is actually working backwards. It's saying if I have a to the m over n, I can break that up in 2 parts. So imagine what that means then as we move into radicals. If I have something like 9 raised to a power of 3/2, we can break that up then. That's the same as 9 to the 1/2 power raised to a power of 3. And 9 to the 1/2 is the same as the square root of 9. So what we're having here is the denominator is telling us the root to take, and the numerator is telling us the power then to raise that answer to. And we'll look deeply at this a little bit as we move into radicals in the next part of this unit. But for now, I want you to really practice with that. Does the denominator tell you the root? Does the numerator tell you the power? And can you break them apart? I'm going to stop here because we've covered a lot so far, and I want to give you some time to dive into this a little bit and get some practice before we move on.